Good afternoon, everyone, and welcome to our first June edition of our seminar. Today we have an old regular, if I may say so. So Fernando has been here. Well, he's attended a lot of these seminars, obviously, but he also, I think, gave probably at least about 3 talks already. Certainly 2, probably 3. I can't remember.
I think two.
Okay, so maybe this is the third.
One together with Lynn about Confluence, and then another one with GReTA a couple of months ago.
Okay, yeah, okay. So, I mean, he has a long history of working in graph rewriting and the interface with logic and algebraic specification and sort of automated reasoning as well. He's been into graph databases more recently, but I think today this talk is not related to graph databases. It's about a particular form of term graphs or something slightly more general than term graphs and the rewriting of those and the compositionality aspects, which apparently are improved by allowing cycles. So I'm not sure how that works, but I'm sure he'll show us. So I think you have to share your screen again, Fernando.
Yeah.
You can't see it at the moment.
Yeah, minute.
Yeah, it's coming up.
Yeah.
Okay, so go ahead, please. We can all see the screen, I think.
So thank you, Raiko, and thank you, Nicolas, for the invitation. So what I'm going to talk about today is about a kind of graphs called DRAGs, which stands for something like directed, rooted, labeled, but then taking only the A graphs, which were invented a few years ago, 2 or 3 years ago by Joanno and Dershowitz. So the aim was to have a kind of, well, that's the outline of the talk. The aim was to generalize term rewriting to graph rewriting. And so they thought that for this, they needed to work with some kind of graph that was a generalization of terms. Generalization in the sense that you could have not only shared nodes, but also loops and anything else similar. So well, I must say also that since they come from term rewriting, so they are well-known persons in term rewriting, you know that term rewriting people, they are not very keen of category theory. So all this work is, so to say, theoretical. Although I must say that probably trying to cope with this kind of graphs categorically, it would be difficult because of taking into account the specificities of the approach. So as I said, the idea of these DRAGs is to have a generalization of terms, or saying in a different way, to have a kind of labeled graphs with variables and roots. In what sense is it a generalization? Well, first of all, nodes or vertices are labeled by function symbols, which have a certain givenarity. And this means that for every node in a drag, the outgoing rank of the node, the number of outgoing edges from the node is fixed, and it's ordered. So it's the first, so to say, successor is different than the second successor, different than the third, etc. On the other hand, well, in trees, in terms as trees, you have a root, which is the root of the tree. So to have something similar here, they decided that graphs would have trees also. And also terms have variables, and so they have variables. To have an idea of how they look is this could be a drag. So you have here two function symbols, which are f and g, some connections between them, and then we have some variables, in this case, just one variable, which is repeated in two different places. For some terminology, these arrows without origin, they are roots, the way we describe roots. The nodes in which we have variables are called sprouts, and the other vertices or nodes are called internal vertices. Yeah, for working with them, we have yeah, in which sense they generalize terms, and not only terms, but also the operations that one can do with terms, especially term rewriting. So when you do term rewriting, you have a rule which is R going into R, and the way you apply it to a given term is you find some place in the term where this root is this L is part of the term. Over this term, over L, we have what is called the context, which is what is in the tree over the term, and then the term may have variables which, when substituted, give you the full term. So the term, the way you apply a rule, is a term where you can distinguish these two parts, the context and then the substitution of the variables. And what you do when you apply a rewriting step is you replace L by R, just in the place where L was. So you can think that in a term, you have, when you are going to apply this rule, you have a piece, which is the context, then the substitution, and then the L that you apply that is more or less in between. So, and when you do the relation between the left-hand side of the rule and the original term is that, well, the C is put on top of L and the context put on top of L, and then the below you have the substitution of the variables of L. So the idea in drags is to have something similar. But the question is that it's not so, we cannot have this kind of distinction between the context and the substitution, but the idea is that whenever we have a rule, when we have we want to apply a rule, the left-hand side of the rule is in some sense included in the graph. It's included, like in the case of trees, the left-hand side, or in the case of terms, is included inside the tree. Here, it's included inside the inside of the graph. Included means that there is a context, which is at the same time the context and the substitution. It's the same thing, where you can connect this context to L, so to give the term where you are going to apply the rewriting step. And in this case, what you do is, when you apply, what you have is that the original term can be seen as the composition of L and this context. The applying the rule would mean replacing this L by the right-hand side of the rule. Yeah, let us see this in a bit more detail. So in a drag, you have a drag as includes a set of vertices or nodes. We have a multi-set of vertices, which are called the roots that the roots of the drag. We have this set of sprouts, which are the vertices holding variables. And we have a labeling function for our vertices that, in the case of internal vertices, which are not sprouts, the label is a function symbol, a function symbol together with an arity, and in the case of sprouts, it's a variable. It's a variable. The labels are variables. And then we have what we call a successor function, which denotes so for every vertex, it gives us a sequence of vertices, which are its successors, or the vertices that are connected to B. From B to this vertex, we have an edge. We have two operations. One is not very interesting, but it's useful sometimes, which is just the sum, which is a disjoint union of drags. And we have composition, which essentially means when we have two drags and we compose them, essentially this means connecting variables of one of the drags to roots of the other drag, and vice versa. So interconnection works symmetrically on both drags simultaneously. For more detail, in order to define composition, we use what we call a switchboard. A switchboard is just a concept, a pair of mappings that tells to each a pair of mappings, the he. So if we call the switchboard he for D and D prime, then he D is a mapping from sprouts of D to roots of D prime, and he D prime is a mapping from sprouts of D prime to roots of D. These he's are partially injective functions, and when we compose these two drags, we may say that D prime he is an extension of D, or vice versa, as we prefer. That must satisfy three basic conditions. One is that if two vertices have the same label, two sprouts have the same label, then the switchboard is defined on both of them or on none of them. It cannot happen that one is it's defined, the switchboard is defined for one of these vertices and not for the other, and vice versa. And the other property, which is more important, well, this one is important, but it's that in principle, since we have not direct restrictions on how he is defined, so when we connect, for instance, a source of V of D to a root of D prime, this root may be a root for a sprout itself. And this sprout may be connected to another root of D, and this root may, which may also a sprout, which may be connected to another root of D prime, etc. And so what we ask is that this kind of close disclosure of he does not induce cycles, so that we don't have any cycles in this definition. Let us see an example, some examples, not just one, for instance, because this operation is quite important technically. So one very simple, so we have a sprout which is just g of x, and another sprout that is f of y, and we map x to, this is a typo, to 2, then we make it the drag g of f of y, which is quite obvious. Something a bit more complex. So we have, for instance, this drag where we have f with 2 roots and 2 successors labeled with the same variable, and another drag with g and 1 variable, so g of y. If we map x into root 3, so this means x to g and y to 2, then what we get is a drag where both successors of f are the same vertex g, so g is shared by both successors, and in addition we have a loop. So this happens because these two x's go to 3, which means we have g shared by the two branches, by the two, and since y goes into 2, and y is the successor of g, and goes into 2, which means that y is f, then we have this additional h from g to f, having this loop. So, well, we have a couple more, but I think it's no need to look at them in detail. And then a rewrite rule is, as expected, just a pair of drags that we write as usual L arrow R, such that the roots of L and the roots of R coincide, and the variables of R are included in the variables of L. And the first condition is needed because, as I said before, the idea is that when we apply a rewrite step, we are going to replace L by R. And this means that all vertices, all sprouts that are connected to roots of L must now be connected to roots of R. And so they should have the same root, sorry. And on the other hand, the fact that the variables of R is a subset of the variables of L, this is not so much a problem to have this condition, but it's a quite traditional interval writing system, but it's not essential here. So the idea of rewriting is, as I said before, as I explained before, is the following one. So we have that D rewrites to a drag D prime, and rewrites into D prime, if D is the composition of some drag W and L. That was the idea, that L is in a way included within D, and the result is W, D prime is W composed with R. So we replace L with when doing the rewrite step. In principle, as you can see here, the idea of matching is that given the left-hand side of a rule L and a drag D, in principle, to see if we can match L to D, we would need to find this complement W, this extension W, and this extension of L. Actually, it may be more simple because, as one would expect, we have that given these two drags, L and D, there exists a monomorphism M from L to D, so a matching morphism, if and only if there is an extension C of L, such that C composed with L is equal D. So this relates the traditional way of matching in graph transformation with this kind of matching in drag rewriting. So the idea is this one, as I said before. So we have C and L, C composed with L. This is the drag in which we apply the transformation, and the result is C composed with R. For example, a very simple example. So suppose that we have a drag that consists just of F with an arrow to F to another vertex, also labeled by F, and also a backward edge going from the second F to the first F. So we have here a loop. And suppose that we want to apply the rule that writes the rule that F of Y rewrites into Y. then obviously we could apply this F to the first F, to the matching of this F to the first F or to the second F. Suppose that we do it with the second F. Then the way that we would proceed for the rewriting step is as follows. So we will see that this drag is equivalent to a drag where we have F with two roots, 1 and 3, and X in here, so new variable X, and such that we can see that composing these two drags, X goes to F, and Y goes to this F, yields exactly this graph, this drag. So after applying the rule, what we do is just take the same context with the same keyboard, and we apply it to R. We compose it, and the result would be the drag F with one root and a loop from F into itself. Okay, something that it's not common to see on graph transformation is unification. There are some very old papers where some form of unification was studied, but since we don't have variables in general graph transformation, there is no really need for unification. No, it seems so. Well, there's some work by Detlef and someone else on unification of symbolic graphs, but in this case, the variables are completely different from the variables that we have here. So in the case of trees, of terms, so when we have two terms, T and T prime, and we want to unify them, unifying them means finding some kind of substitution that when applied to T and T prime leads to the same term. And in this case, we say that sigma, the substitution sigma, is a unifier of D and D prime. In here, it's slightly more complex for a specific reason, for some reasons. So in here, the idea also would be we have two drags, U and V, and we want to apply also some kind of substitution or something similar that makes them equal. The question is, there are two questions here. The first one is that in here, when we define unification of two terms, so to say, we think of unifying T and T prime from the root of T and T prime. So we take T and T prime and we try to match T and T prime from the root to below, and applying substitution, we try to find the unification. But here, in the case of drags, we don't have a root as in a term. Actually, we have more than one. What we do is to consider unification to what we say a set of partner vertices, which are some vertices that are in U and some vertices that are in V, exactly the same number, and that in principle, they are going to be like the roots of the tree in order to define unification below it, below these terms. But at the end, the final result should be the two graphs should be the same. And the second issue is that, as we have seen, substitution here is just composition. So what we want to do is to have in order to unify U and V, we are going to define two extensions, C for U and D for V, such that the two drags obtained are the same one. or actually isomorphic. And in this case, we would say that these two extensions are a unifier of U and V. So to be more precise, so there's this idea of partner vertices. So partner vertices is there are at least two lists of equal length, of vertices of equal length, of internal vertices of U and V, respectively, such that no two vertices in any of these lists is a successor, direct or indirect successor of U prime is direct or indirect successor of U. So they should be, so to say, independent with respect to the successor, the successor function. And then a drag unification problem is a pair of drags together with a list of partner vertices, set of partner vertices, and a solution or a unifier is a pair of rewriting extensions of C and D, of U and V, respectively, such that the results are isomorphic. Now, in order to define a notion of most general unifier, we define as usual a subsumption, which in this case, we say that a drag U subsumes a drag V if and only if there is an extension of U such that V is equal to the composition of this extension with U. And subsumption, as usual, is a quasi-order whose equivalence is variable renaming, and the strict part, and the strict part is well-founded. So let us see what is the unification algorithm that we have developed for here. So the algorithm follows two steps. The first one is more or less similar to what we do in term writing. The second one, we don't have it in term writing, and actually is quite complex. It took us quite some time to find that part. So the first idea is that the first step will consist in defining a congruence on the vertices of U plus V. So the idea is that we identify vertices of U with vertices of V, and this identification will be used then to build the unifier. Initially, so in particular, each pair of partner vertices should be, according to this congruence, should be congruent. And the way we are going to do it is by taking the two drags and marking the vertices with marks that are natural numbers. These marks are going to be in red or in black. Red means that they don't have propagated yet. So for an equivalence on vertices to be a congruence, it must happen that if two vertices are congruent, then their successors must also be congruent. And so the idea is that when we know that two vertices are congruent, we are going to mark them in red. This mark, we are going to mark with natural numbers, some natural numbers in red. And when we propagate this equivalence, this congruence to the successors, then we are going to put these marks in black, but we would add marks to the successors that would be in red. So to be more precise, so initially we assume that all partner vertices hold red marks with which would be numbers 1 to n if there are n partner vertices. And this, as I said, they are going to become black after being propagated. And we assume that we have a global counter C that produces fresh new marks for marking differently the different nodes that we are going to be marking. Now, the rules that we apply for defining this congruence are the following ones. So the first one is propagate. That is what I just said. So if we have two nodes, U and V, with the same mark I in red, and they have as successors S1 SK and T1 TK, then we are going to mark each of the pair SJ TJ with a mark C plus J. And we are going to turn the mark I that we had on the original vertices into black. Now, if we have a pair of vertices, S and U, where S is a sprout labeled by some variable X, we know that this vertex is not going to have any successor. So we can put in black both marks. We can put I in mark into black. And merge, if we have two vertices labeled with the same variable, then they are going to be equivalent. So we mark them with label. I'm going to add a mark C plus 1. Following rule is
Fernando?
Yes.
I have a question. So I'm trying to understand. I mean, before sort of understanding really the mechanism for the smallest congruence, I'm trying to understand how you generalize the notion of congruence here. To graphs, and I see two different sort of alternative interpretations here potentially. First of all, because you have term graphs, they are labeled by.
Well, they are not term graphs because we have loops.
All right, so not term graphs, but they are the graphs are labeled by operations of a signature. So in principle, you could think of using a kind of algebraic notion of congruence by using the operations that are the node labels and somehow think about those. But I'm not. But what you're suggesting sounds more like a kind of navigation-based property than the kind of traditional algebraic view of congruence. So can you sort of elaborate first before we talk about the smallest congruence in general? What is a congruence on?
Yeah, a congruence here in drugs is if I don't have the definition here, but roughly is an equivalence relation on vertices such that if two nodes U and V are equivalent, then their successors are equivalent.
More than one, right?
Yeah. So for instance,
so any let's say if A, or let's say if A has two successors and B has one successor.
No, they should have the same number of successor, because you cannot have that two terms are equivalent if they have a different label.
Oh,
so they should have
because
the same label, and so they have the same arity.
Okay. Right. So that means the left successor of F is then needs to be equivalent to the left successor of the other.
Yeah, exactly. So
okay.
So the idea is that, so if we think that F has K successors, because F has arity K, and this successor S1 is K, and the successor in the other graph, in the other drag, T1 TK, then S1 must be equivalent to T1, S2 must be equivalent to T2, TK, SK must be equivalent to TK.
Right, and how is that related to, if at all, congruence in the algebraic sense? If you were to use the
well, in the algebraic case, I think it would be the other way around. So if we have that the successors are congruent, so the operands are congruent, and we apply the same mapping, the same operation on both.
Okay.
Then the result must be
you're right. So it would work exactly in the from the variables to the roots, whereas here you work from the roots to the, or from the, you work upward. You work downwards. In the other case, you would work upwards.
Yeah, exactly.
Okay. That makes sense.
So
okay, thank you.
Another rule is transitivity, which means that we have that if a vertex U is labeled with marks, has marks I and J, and V has mark I and J, and W has mark J, then this means that all three are equivalent, congruent. All three, U, V, and W would be equivalent. And so to make explicit that V and W are equivalent, congruent, then we mark this pair with another mark that is C+1. So in red. And so this may create a new. So these are the rules for building this congruence, this smallest congruence. And then we have a certain rules that detect conflicts, that detect that the terms are not unifiable. So the first one is that if we have that U is labeled by I and V is labeled by I, then they should have the same label. So if they have a different label, then they cannot be unified. The two terms cannot be unified, and we would fail. Another case is what we call internal conflict. So two internal vertices of one drag cannot be equivalent because unification only add, so we only add new nodes to new vertices to the two drags, so to make them equivalent, to make them isomorphic. But we cannot, so to say, join to make equivalent two internal vertices of the same drag. We cannot join them into a single vertex. So this means that if this is the case, the algorithm will fail also to find a unification. Sorry. And the last one is a lack of root conflict. So something that I didn't explain when defining composition is, when defining composition, let us see in the examples. When defining composition, when we connect in this case, we bind in this case variable x to root 2, then x disappears, and this root is consumed, and that's why we get the result, the term IGFY, GFY with a root on G. But this means that if we want to bind X to a certain node, a certain vertex like F must have a root. If it hasn't a root, then we cannot make this composition. And so when trying to make the unification, we may need to bind some node to some sprout to some root, so to some node. But if that node doesn't have any root, then we cannot have this composition. And in this case, the algorithm fails. So that's what we do in here. So in the lack of root conflict, essentially says that if we have a situation where we would need a root in one vertex and there is no root, the vertex in this case U is rootless, then the algorithm fails. The two cases are two situations in which this happens. I won't give the details of this, but the idea is this one. And so after we have this, after we have computed this equivalence, this congruence, then we can build a new, the most general unifier as the two extensions C and D as follows. So here I show this case of C, the case of D is going to be equivalent. So the context that would be the context C would have a set of nodes VC. This set of vertices consists of the following vertices. So on the one hand, if we have an internal vertex in V, so there's a problem with notation here, with this V for vertex and V for the drag. Sorry. So if we have a vertex in V, which is not congruent to any internal vertex of V, this means that this vertex is not in U. If it's not congruent with any internal vertex in U, this means that this vertex V is not in U. And so in the unification, we will need to have a copy of this vertex in U. And the way of having this is to putting it into the context. So this is one case. The other cases are sprouts that we will need to add into the context C. So for instance, for each sprout, so for each vertex U in U that has a root, for each of these, we are going to have a sprout that we call S sub U that is labeled with variable X sub U. The reason is for having this sprout is rather technical, so I won't be going to it, but the following one is maybe more clear. So if we have a root, R in U, and there exists an internal vertex in U that is congruent with R, then we are going to add an unrooted sprout SR into the set of sprouts of C. And the idea is that we are going to need to connect this root that we have in U, this root R, this sprout R in U with the vertex to which is congruent, and the way to do it is via this sprout that we add to C. And if we have an sprout that whose in its congruent class there is no internal vertex, this means that all these sprouts that are in this congruence class are going to be just a single sprout in the result of the unification. And in order to put them all together, we add this S sub S into the congruence class, into C. And the key that is going to be defined on these sprouts and roots of C and U work as follows. So if we have for the sprout X sub U that we have in the first case of sprouts, we are going to link it to bind it to U for its sprout. Then in the case of XR, we are going to bind it to R, and for its sprout SR in the case of sprouts of U, then for its X, we are going to bind it to SU if this sprout S is congruent with U. And and sigma u. So I'm afraid you cannot follow me, so I better skip this. But the idea is that we are going to implement here all the connections that are needed to build the unification. In a minute, we are going to see an example. So in the case of the roots that we have in C, in the context drag, is so what we need is to have the right number of roots for its vertex in C, and well, we have computed this in every case, and but I'm not showing it to you here. As an example, if UV is one internal vertex that we have added to C, then this vertex is going to be equipped with R plus N roots, where R is the number of roots of V, and N is the number of roots of sprouts in V that are congruent with V, because all of them are going to be connected to this. And so we need R plus N roots, so that at the end we have R roots for this vertex as the roots that the corresponding vertex in V has. And then finally, the way of defining the successors of its internal vertex is if we have that one vertex V that is in V but not in U, this means that another vertex similar to this, a copy of this vertex, would be in C. So if the successors of V in the drag V are V1, Vk, then we define the successors of the copy of V in U as the tuple W1, Wk, where W1 is equal to the root to V1 if Wi is equal to Vi, not to UVi, but to Vi, if UVi is in C, and otherwise is some of these sprouts that we have added into C. So suppose that we have here these two terms, these two drags, sorry, that we want to unify. And suppose that we have as partner vertices just G, this no vertex G, label G with this one. And so the marks correspond to the marks that have been computed by the algorithm. Now, let us see how we would build the context so that they unify. So in here is the term, the drag U, and here's the drag V. And so here we have this extension is going to be a drag having an internal vertex A with one root and a sprout label Z there with two roots 3 and 4. Now, why this is so? Well, A is one sprout, some internal vertex in W or in V, in this vertex, that is not in this vertex. So we must add a copy, and this copy will need to have a root in order that at the end everything fits well. And in addition, we have that we have that this node is a rooted node, and for this reason we add a sprout that is going to be bound to this node by here. So in particular, as you see here, Z the variable is connected to 1. And the two nodes X and Y that we have in here are connected to node 3 to 3 and 4. So to 2 and this is wrong. This is no, sorry, it's okay. X is connected to 2 because X is in here and it needs to be connected to the copy of A, so to replace it, and the other Y is going to be connected to this Z, so that everything fits, and the result would be this drag, the result of this composition. Similarly, if we compute the extension for the second drag, what we get is this context, this drag, this extension, which has also 2 vertices, but in this case there are 2 sprouts. And if we compose this with these 2 sprouts with this vertex, with this drag, then we get exactly the same drag, which would be the unification of both drags. So what we have proved for this is that that if on the one hand, if a unification problem has a solution, our algorithm computes its most general unifier, and otherwise it fails. So this means that it doesn't have a solution, it will fail, according to our algorithm. So this means that the algorithm is complete. Moreover, there is a single most general unifier, and to compute it, we have in the worst case, we need quadratic time and quadratic space complexity. So this is for unification, and the last part is confluence. So we know for graph transformation from 1993 from Detlef that confluence on terminating graph rewriting systems is undecidable, but more recently, Bonke and other people, including Fabio, proved that for graph rewriting systems or graph transformation systems with interfaces, it is decidable. Confluence, it is decidable. The explanation they give, or the conjecture they give as an explanation, is that actually the situation is similar to what happens in term writing. So in term writing, confluence for terminating rewriting systems is decidable in the general case, but confluence for ground term rewriting, that is when terms have no variables, is undecidable. And so the interfaces will play the role of variables. And well, this conjecture is in a way confirmed in the sense that in our case, confluence is also decidable. And we have variables. Well, you know that the standard way of computing confluence is by taking local confluence, that we know that if the rewriting system terminates is equivalent to local confluence. And what we do here is relatively straightforward because we follow essentially what the way this is shown for term rewriting systems. So term rewriting systems, typically you consider 2 cases when you have to check if given 2 applications of 2 rules to a given term to see if they converge. We consider typically 2 cases. One where the redexes of the two rules are independent, share no nodes of the tree, and in this case we know that there is no problem of confluence. Here is the same. So in this case, if this is a drag, we may have exactly the same situation. And this case, in our case, it's equivalent to saying that this drag can be divided into two parts that when composed would yield the original drag, one including L and the other including the rest of, so one including L and the other one including the left-hand side of the other rule G. And the other case, that is the general case, that is dealt with in term writing by computing critical pairs. Here it's in a way similar. So we have that the binding, the application of the two rules, the matching of the left-hand sides shares some vertices. What we can do is compute the most general unifier of L and G with respect to partner vertices, the pairs of the pairs of vertices that are shared. So we can compute this most general unifier of L and G and prove that the original drag is the composition of this most general unifier and some additional context C. So taking this into account, the proof of confluence has two lemmas. The first lemma is when there is no overlapping between the two radixes. So in this case, suppose that we have U, a drag U, that can be decomposed into VW, and we can be rewritten by the first rule, L times R, and W can be rewritten by G times GROD. Then this means that given the original drag, we can apply the first rule on the first component of the second rule in the second component, but then afterwards we can apply the other rules into the components that we hadn't changed. So in this case, we could apply GD to W, or here we could apply LR to V, and the result would be the V prime composed with W prime, and so we have that this is confluent or locally confluent. And in the other case, if we have that we can rewrite U into S and T using the two rules. So if they share some internal vertices, then we know that there exists some, can prove that there exists some partner vertices, set of partner vertices, and the extension C and E, such that U is equal to L times C and G times C. And so we have also that this would be confluent if this is possible. So the critical pairs are just as usual pairs, where if we have this overlapping between LR and C and GD, so that we can extend them to a most general unifier, then a critical pair would be the C composed with R and C composed with R and D composed with E. And these are the cases where no confluence, then we have no confluence. And well, what can be proved as usual is that if all critical pairs are confluent, then and the set and S is a terminating rewriting system, then this is equivalent to the confluent of all S if all the critical pairs are confluent. And thank you for your attention, although I haven't been very fine in explaining this, sorry.
Okay, excellent. Thank you very much. Yeah, I think we got the main idea. I mean, the technicalities are always tricky, but I think the examples are helpful. Yeah, so I'm trying to understand. So can I see the chat here? Yeah. So I'm trying to understand essentially under which conditions this works slightly more generally, because there are sort of related notions of graph, I would say, which maybe are expressed slightly differently, but have kind of fundamentally the same structure, such as if you have hypergraphs with interfaces, for example, labeled hypergraphs with interfaces, which have, let's say, if they have input and output interfaces, then you could also have a notion of a composition that works in the same way, or you have one like I mean, Fabio has been developing, for example, in string diagrams, where you have the sort of more explicit operators in order to represent the wiring that you add to the composition operation, where you say which nodes are, or which interface nodes are basically connected to which other interface nodes. So I'm trying to understand if this technique would work, specifically the computation of these unifiers would work for any graph structure that essentially has sort of input as output interfaces, because internally the graph structure is arbitrary, isn't it? So you don't have restrictions. You can have arbitrary loops and things like that.
Well, there is one
as long as you have something like nodes labeled with operators that have fixed arities, or maybe alternatively hyper edges that are also labeled with elements from a signature, which also have fixed arities. So fundamentally, you have the same information about the structure. So I would imagine maybe that the kind of computation of most general unifiers could also work in that case. Let's say hypergraphs with interfaces, or with two interfaces.
Yeah, well, yeah, string diagrams are quite close to this, and in general, graphs, any kind of graphs with interfaces are close to this. Sometimes you see some restrictions with respect to what we do here, in the sense that when you think of connecting input and output interfaces, as we connect drags to sprouts with roots, sometimes so circularity is not thought of. In other cases, yes. So in this sense, they technically look quite similar. What it may change, and I don't know up to which point these changes would affect the application of these results to this other framework, is this restriction that of the arity of function symbols, which means that the number of successors of each vertex is fixed, and moreover the order matters, the order in which they are matters.
So I was thinking of hypergraphs. So if you have a hypergraph, and the hypergraph is labeled by hypergraph over a signature, I think you have essentially
a hypergraph. So you can relate So vertices with hyperedges, vertices in our approach with hyperedges, and there would be some kind of probably direct translation from one formal list to the other. And in the case of hypergraphs, typically the vertices to which they are connected, the nodes to, they are also a sequence. They are not. The fact that, you don't have this constraint that all vertices with the same label must have exactly the same number of successors. Now, for sure, this would matter for when computing the complexity, the cost of the algorithms. So, if instead of if the successors are not ordered, then this is equivalent to having commutativity on function symbols, and then computing unification with commutativity on terms. It's much more inefficient. I don't know exactly of what order. And so it would be here. But so in the case of hyperedges, you don't have this issue. The fact that two hyperedges or two vertices in our case may have different number of successors, I don't know how this would affect, for instance, defining unification. One would need to be able probably to add successors to one graph in order to unify with another graph, with another drag. So because if we have a graph which is includes or a hypergraph, but let's say a graph, we have a graph consisting of one node A that has two successors and another node A prime with the same label having three successors. So one graph has A and two successors, and the other has A and three successors. One would need to decide whether these two graphs are unifiable, if it's possible to add a successor to the original to the first graph. And I don't know how this would affect the overall algorithm.
Yeah, I mean, the standard notion of hypergraph, of labeled hypergraphs, in the standard notion of labeled hypergraphs, the labels actually have arrow keys as well.
Yeah, yeah, I know. Yeah.
So they would fix the number of
if they fix
predecessors and successors. So in that sense, it would be pretty much like your operation symbols.
Yeah, then probably the same kind of construction of unification would be similar. It depends also on how composition is defined. And I say this because I don't know how standard is composition how it was composition in hypergraphs with hypergraphs with interfaces. But in the case of drags, in what I have presented today, I have used a kind of composition that is the kind of composition that we were using when we first when we worked at this paper. But nowadays we have a different notion of composition that we have decided that is simpler. And for sure, we can build a unifier, most general unifiers, in a similar way, but not exactly the same way. So we haven't done it yet, but most probably we would need to change some things, some small things, to make some repairing in some places. And this might happen also, but otherwise probably one could have some kind of unification for string diagrams in this sense, or in general hypergraphs with with interfaces, I guess.
Okay, cool. So right. So that answers my question. I think so. Barbara had a question, and then Fabio, and I think Carlos Zapata just posted a note on the chat. Maybe he can sort of say something about that in a moment as well. But maybe Barbara first.
Okay, so thanks a lot for the talk, Fernando. So I wouldn't worry it, but I think it was quite clear. So very, very understandable. So I have a question about this unification. Does your notion of unification subsume the standard notion of unification for terms? I'm asking this question because in the terms you have the same substitution on both sides, whereas you could have different contexts that perform different substitutions or replace the same variable but different things.
Yeah, well,
same notion or different?
Well, almost the same. So in terms, usually you have just one substitution, but this is a convention that simplifies things. So if we have two terms that are the names have been named apart, so that the variables are independent in one case and the other, so they have different names, then it doesn't matter to have one substitution or two of them. And that's the standard way.
True, that's true, but it is a different term. For instance, you cannot unify x and f of x in standard substitution.
Yeah.
That's
so this is the difference.
Yeah.
So the difference is that we don't have the it's called the name of this condition.
I know what you mean. It's important for prologue for the prologue unification. What's it called? Yeah.
So this condition that you cannot do this unification because this would mean going into infinite terms or something like that.
Yeah.
So here we just have a loop. So if we have f of x and x, then, well, as you saw in one of the examples, then we create a loop.
Okay, so you can unify in these cases, but you would get a loop, and so you do not strictly subsume term substitution, but you say, okay, in this case, it should be different. Okay, thank you.
It would be more or less similar to something, to rational term unification or something like that. It would be probably more related, because in a sense, but here they are not exactly on rational terms, but it would be something similar. Yeah.
Sorry, I'm on mute. Fabio, you want to?
Yes. Okay. Thanks again for the talk. No, I was just a note about composition. The fact is that usually when you do a graph composition, you collapse the input of one of the graphical interface with the output of the other. Here instead you have some kind of cycles where you can, how can I say, feedback also the other terms, which is for sure more general than what is usually done. I mean, in the end, the kind of hypergraph composition which is used in string diagram and so on is just co-span composition.
Okay.
Roughly. Okay. While here instead, not only you compose one input with the output, the input of A with the output of B, but also the input of B with the output of A. So it's like that, I mean, you're much more general. In hypergraph, you should have some kind of specific composition, like, I don't know, first composition, then some trace or whatever. It's clear that this way is much more general. I assume it makes things also much more difficult, right? Because
but Fabio, sorry, maybe I'm sort of naive, but my instinct is that if you have the right combinators, like today,
yes, of course,
blah and so on, you can basically produce the same
absolutely
in the end. It's just that here you have the wiring information or the rewiring information in that argument, whereas in the other case you have it in kind of basic hypergraphs that you compose, right?
That one I perfectly agree. The point is that in general, the composition is just one input with one output. I mean, series of input, series of output. Of course, you could build more complex operators with actually taking into account also the other bits and to compose them with. I mean, if you don't have what is called the Frobenius structure, I mean, duplicator, coduplicator, and so on, you put a trace. There is recent work by GReTA and others on monoidal closed string diagrams, for example. Or otherwise, of course, I mean, it's just a matter of how complex you want your operator to be. Let's say the basic one is just input and output. If you want also to have this kind of loop, which is here, then you can do, but of course you have to be much more, how can I say, it's much more difficult to understand exactly which are the property of the larger operators, okay? While instead for the simple composition, the properties are quite clear.
Yeah, I must say that something I've been doing or trying to do is to express these ideas categorically. So not for drugs, but some arbitrary category of things that should satisfy some properties. And part of it was looking for what kind of properties one would need. And so the problem, so this work is not finished, and actually I had almost finished, but then we changed the notion of composition, and accordingly I decided that I had to change the notion of composition in that case, and this I haven't done anything. So, but the notion of composition that I'm used here. So I managed to define some kind of diagrams, more or less complex diagrams that would lead to the result of a composition. And with respect to the kind of conditions that I would need for the category, so I didn't need to have any form of adhesivity. Well, not exactly. So maybe MN adhesivity would work, so would be a sufficient condition for having it. Standard kinds of just adhesivity was more than needed. So for instance, I could define a transformation of simple graphs in this term. So the idea is that defining transformation in terms of this kind of composition, like not by standard push-outs, or well, obviously push-outs or co-limits play a role in there, but as I said, I could deal with simple graphs, which in principle with adhesivity you can't, but with MN adhesivity you can. So it might be, maybe it's equivalent to the conditions to what I had with what you have with MN adhesivity. This I don't know. But so it was a bit complex, but not too complex, the definition of composition in that case. And yeah, but I cannot show you anything because it's not finished. And hopefully I will finish it sometime.
Thanks, Fernando.
Yeah.
Okay. So I don't know. I mean, Carlos, do you feel it's worth telling us a bit about the context of your compositionality problem, or is that too early? I mean, I leave it to you if you want to give us a brief.
Yes. Hello. Absolutely. I would just wanted to mention that, because it was mentioned in passing that some hypergraph compositions could be understood here. I mean, I didn't follow every single detail of drags, but I did see some general parallels. So just to mention that I am trying to work on these kinds of general settings where you have a way of doing compositionality that is very parsimonious, So drags in particular should be encompassed, and graph compositions of any kinds should be encompassed. And the whole challenge is to try to do it with graph rewriting or hypergraph rewriting itself. So seeing disconnected or unconnected graphs as just other kinds of graphs, and you're applying rewrite rules to those and so on. So it was just a note in passing. I don't think it's particularly directly relevant to anything of your talk, Fernando, which I enjoyed actually, by the way. It was a nice space for someone who's not familiar with this material. And yeah, so just to mention that I am working on that at the moment, and at some point I'll have some more relevant paper that I can share with this community, and then maybe we can discuss it at some point later on.
Let us know when you get there. It would be good to hear what.
Yeah, thanks.
Okay. Excellent. Nick, did you want to say something?
Yes. So first of all, thanks, Fernando, for the talk. And Carlos, of course, let us know. Then you might want to give a GReTA talk, maybe. So Fernando, I found quite interesting. You had this comment at some point in the talk that this way, basically, when you can decompose a drag with one of those rewiring switchboards, that you can basically say there's a monomorphism between a drag, say L, and a drag D. Whenever you can find that D decomposes in this way as L, some rewiring switchboard chi, and then a context C, yes. And then the next time you said when you are looking for most general unifiers, I mean, at first point I thought it might look a bit like you look at something which classifies all possible cospans of monos, let's say, at least. But then you said no, in fact, this algorithm might fail. So intuitively, I would have thought with this concept of monos, you said it's always possible to simply embed two drags disjointly. So presumably the failure of that being then, if there's no other way to join them, the most general unifier might be that you cannot always embed the disjoint union of two drags. So what exactly is the failure? Is it because you can make these loops, or?
No, well, no, not exactly. Look, well, partly is the same kind of failure that you have in term unification. So you cannot unify f of x with g of x because f and g are different functions. So that this is one of the conditions. So
but then I would think that the unifier would be having them both in parallel, and simply this can never happen because when you do the context extension, you
no. So and here comes the key point. So this would be possible if the list of partner vertices is empty. So that's part of the role of the partner vertice. So you fix, it's like saying at least this list of vertices should be shared in the unification, should be considered identical in the unification. And you choose,
that is my question. Why you would ask this? That was exactly my question. Yeah.
Well, because well, for instance, one could ask, and this related with this, how what is the role in a sense of how much time, what is the complexity of checking for a confluence? Okay.
So know. So you're saying that you modified something which might be a valid concept of MGU in order to have a better algorithm.
No, wait. So in order to decide whether, so in order to compute the critical pairs, so when you have two rules, then for each possible choice of partner vertices, you will have you may have a different critical pair. Because you are saying in this case which so to say which vertices are going to be overlapped by the two rules.
But there might be none. So
there might be none, but then you don't need to compute any is the case where the two redexes are completely separated, and then this is directly, you know that this is directly confluent, that you don't have any problems. But when you want to see if you can apply two rules to a given drag or to a given term, then The problem is always when the red excess of the left hand side of the two rules overlap in some sense.
Mhm.
And this overlapping is the one that defines the partner vertices that you are going to use for building the critical pair.
It is just that somehow I'm comparing this, especially if you said you can do some form of simple graph rewriting. In simple graph rewriting, you would exactly have a maximal general set of unifiers, which always includes the disjoint union, even if you work with, so in Fernando's encoding, he has either the version where you have regular monos as matches, or that you have a non-trivial multi-sum construction, or you have monos, and then you in particular have just a standard additivity construction. So I mean, in both cases, you need the disjoint union as one of the elements in the most general unifier. So I was wondering, I mean, in particular, you would have a whole set of unifiers, not just.
Yeah, well, in graph transformation, usual standard graph transformation, yeah, you build the critical pairs, including all possibilities.
Mm-hmm.
Actually, if they don't overlap, if the two rules don't overlap, then you are immediately going to show that the two applications are parallel independent, and so you are not going to build a critical pair out of these two applications.
Well, sure, but I mean that is one non-trivial statement then, which you need for the.
So it's the same here. So instead of saying this in the case where there's no overlapping, there is we have parallel independence. Here there's no notion of parallel independence, but we just know that this is not a case where we have any problems of confluence, and so we only care about the situations where they overlap. And for this, we need to check all the possible sets of partners vertices. Actually, there is a question that I was making myself, because I have been working on the two sides, so with Lean and on Confluence, general Confluence, and in here, and I was wondering the following, the connection between the two notions of confluence in the following sense. So, if in the last approach to checking confluence, there is this idea of instead of checking critical pairs, we check parallel. What's the name? Parallel
independence
conflicts. Parallel conflicts.
Parallel conflicts. Okay.
We check conflicts, the minimal set of conflicts, so initial conflicts. We check the initial conflicts, which is the which we have proved is the set of minimal conflicts as the minimal set of critical pairs that we may have with respect to cardinality. So if we have 10 in a specific case, then there cannot be a different kind of another kind of construction of critical pairs that gives you less than 10. This is proof. But we know that previous versions, the original from Detlef, and then afterwards the one from Lin, and also myself and Hartmut, with I don't remember the name of these critical pairs, but you are close to the initial conflict case, but still you have a few more critical pairs. Now, in this case, in the case of drugs, the way of computing the critical pairs, as I said, is so we take the two left-hand sides and try to unify them with respect to the different possibilities of partner vertices. But now,
so that means that you do have a set of maximally. It's not just one. It's like you have any pair.
A set of critical pairs that for each possible choice of partner vertices, we would have a unifier. Well, possibly, because sometimes there would be no unification. But if there is a unifier, we would have a critical pair. And in principle, this seems to be like having, so to say, the original approach defined by Detlef, where you check all the overlaps, and that's it. But actually it is not, because so whenever there is overlap, the partner vertices, they are not all vertices in the overlap, but only the ones that have no predecessor in the set of partner vertices. So if we have in a set of partner vertices, we have one pair is A something and another is B something, but B is successor of A, then we remove this B. And so this means that the number of critical pairs is quite smaller compared to just checking all overlaps. And I don't know if this is related with initial conflicts or not. It cannot be less, it cannot be a smaller number of critical pairs, because we have proved that this is not possible, but it may be exactly the same number of critical pairs. And this, if this is true, this would lead to a procedure to compute initial conflicts, because so in principle initial conflicts, so to say, a definition that works very nicely, but how to compute them in an efficient way, not having to compute previously all possible overlaps, is not so easy. And actually, what Dean had been trying was to try going from the other kind of critical pairs and then reducing them to making a reduction, but it means computing a bit more. Maybe in this way we could have exactly the same one. I don't know. I haven't checked, but I think it might be interesting, because it would be a simple way of producing the set of initial conflicts, if this would be true.
Very interesting. So thanks so much. Maybe we should discuss more another occasion. Yeah.
Okay,
Right.
so maybe if we finish the main part of the discussion, we can close the official session if you haven't done so already. So Nick, do you want to just remind us what happens next?
Yeah, so first of all, thanks of course for Fernando, also for staying for the discussion, and to everyone who participated. And we'll have the last talk before summer break, before the conference season starts in 2 weeks, on automated generation of domain-specific graph models by Daniel Varro. I hope I pronounced the name correctly. And so I'll just switch off the YouTube live stream. So everybody who still wants to have a quick chat, please stay, and then otherwise just switch it off for the YouTube audience.